in the beginning of this chapter, if you remember, I told you that this chapter shows you the relationship between electricity and magnetism. Even the chapter is called electricity and magnetism. Even if you go to, whenever you go to Form 4 and Form 5 later, all right, when you study Form 4 and Form 5, you will see that there is a chapter called electromagnetism. All right, this is the actual word, electromagnetism. Why? Because you must know, electricity and magnets, they are very, very good friends. Okay, they are very, very closely related. Right? They're very, very closely related. How are they closely related? Hey, you must know. You must know. Okay, electricity can create a magnet. Do you know that? Electricity can create a magnet. We call it electromagnet. Electricity can create a magnet. But not only that, magnets can also create electricity. All right. So that is the relationship between electricity and magnet. Electricity, they can make a magnet, but a magnet can also make electricity. That's how we call that. That's how we make a dynamo. Okay. So over here we call it an electromagnet. Okay, using electricity to make a magnet. That means you don't need to have a steel, iron, cobalt, nickel, whatever. You can create electromagnet, and using magnets only, you can create electricity. We call it a dynamo. This is the way, this is how we created electricity in our houses by using magnets. How? Okay, we have a look later. All right. Now, let's look at electromagnet first. How do we use electricity to make a magnet? Now, an electromagnet is a what we call a temporary magnet. Okay, we describe an electromagnet as a temporary magnet. It's a temporary magnet. Why do we call it temporary? Because it is a magnet that we can turn off and we can turn on whenever we want. It is a magnet which we can turn on and turn off whenever we want. And it can be controlled by using electricity. So when I turn on electricity, I will turn on the magnet. When I turn off electricity, I will turn off the magnet. Right? So it is a magnet which has a temporary magnetic effect. What is magnetic effect? Attraction and repulsion. It is a temporary magnet which can attract and repel whenever there is current flowing through a conductor. So we must have a conductor. Okay, a conductor can be a wire or whatever. Will the magnet be strong? Yes, the magnet is very strong. Magnet is very strong. In fact, even much stronger than natural magnets. Much stronger than natural magnets, right? Electromagnets. Okay, now that's the reason why. Okay, we use electromagnets in the factories. You know, and do you know how they process all the recycled tin, recycled aluminium can, recycled steel, the besi buruk, the rotten, what do you call it, spoiled cars? Do you know how they recycle all these things? Hey, if you need people to carry all these metals using our hands, it would take you a long time, and it would take you a lot of money because you need to employ a lot of people to carry. Besi buruk. Do you know how many thousands of kilo of metals they go through the factory? Okay. Whenever we recycle the aluminum can, whenever we recycle a car, whenever we recycle the computer parts, all those things are magnets. How do you carry these magnets? How do you carry these metals in the factory? You will use electromagnet. It's very, very strong magnet. Very, very strong. Okay, very, very strong magnet. Okay. The best thing is you can turn on and off whenever you want. That's the best thing. All right. Okay, I'll explain this later on. This is part of the came up questions. Okay. Now, let's talk about the conductor. Now, why do you need to have a conductor in an electromagnet? You see, what we will do is we will connect this conductor. Oh, what is a conductor? A conductor is a material which can conduct electricity. So you can use whatever, copper wire, steel wire, iron wire, nickel wire, zinc wire, whatever wire, as long as it is a conductor. All right. So what will we do with the conductor? Okay, please bear with me a while. You may be sleepy, whatever. Please bear with me. I have limited time with you. Please listen. All right. Now, whenever you have this conductor, right, you will pass electricity through this conductor, right? You will turn on what we call a power supply, and it will produce electricity, and it will pass the electricity through the conductor. So there will be electricity going through this thing. When I turn on the switch, of course. All right. Now, whenever you turn on the electricity and the current flows through the conductor, you must know a magnetic field will be produced around the conductor. Let's refresh back. What is a magnetic field? Magnetic field is an area where there is magnetism. It is an area where there are magnetic field lines. What has a magnetic field? Magnets have a magnetic field. So if a conductor can produce a magnetic field, what does that mean? It means that this conductor is now a magnet. Understand? So you can see here, there are circle shapes on the cardboard. What these circle shapes show you are actually the magnetic field lines created by the conductor, by the wire. All right, when the wire, of course, this magnetic field line will disappear when you turn off the electricity. But whenever you turn on the electricity, you will produce this magnetic field. Of course, if you ask me why is the shape in a circle shape, now you must know, like just now, we looked at 3 different types of magnets, right? We looked at the bar magnet, a horseshoe magnet, matador magnet. All of them had different shapes of the magnetic field lines. So one thing you must know is that magnetic field lines, the pattern, the shape of the magnetic field depends on the shape of the conductor. If the conductor is in the shape of a wire, then it will produce magnetic field lines in a circle shape. All right. If the conductor is in the shape of let's say a coil, a spring, then it will produce, right, a pattern like a spring. Right. So it depends on the shape of a conductor. Right. Okay. How can we know where is the north or south pole? Very good question. Very good question. We'll look at that later. Okay. I think in the next slide. In the next slide. Okay. Let's go to the next slide. Okay. Okay. Here. Okay. So Juni asked me, how do we determine the direction, or not the direction, the poles? How do we determine the poles of the magnetic field? Okay. Now, first things first, let us study a straight conductor first. That means it's a wire, a straight wire. A straight conductor. Now, you already know that a straight wire or a straight conductor will produce a circle shape, circle magnetic field pattern. Now, either North Pole or South Pole, not that important yet. What is important is the direction of the magnetic field lines. Correct, no? Because when you study magnetic field lines, you study about direction. North going to south, right? You learn about the direction. So now let us know the direction of the magnetic field first, okay? Now, the direction of the magnetic field lines depend on the direction of the current in the conductor. Because whenever you have a conductor, you know that current can either flow from the top to the bottom or from the bottom to the top. That depends on how you connect the wires from the power supply. If you connect positive here, negative here, then the current will flow from the top to the bottom. If you connect positive at the bottom and negative at the top, you will produce a current from the bottom to the top. So the direction of the current flow depends on how you connect the wires. And the direction of the current flow, either from the top to the bottom or from the bottom to the top, it will affect the direction of the magnetic field. The direction of the magnetic field can be determined by a technique called the right hand grip rule. Okay, so what does the right hand grip rule tell you? Right hand grip rule uses your right hand. So all of you, please take out your right hand right now. Take out your right hand right now. Right hand, not left hand. You may see I'm using right hand, but you may see on the screen I'm using left hand, but it's the right hand. Please, right hand grip rule, use your right hand. Now, what does the right hand grip rule tell us? Okay, open up your hand like this with the thumb open. You close your other fingers, let the thumb open. This thumb will be the arrow pointing towards the direction of the current. Understand? Your thumb will be the arrow. Just imagine you draw an arrow on your thumb. Okay. If you cannot imagine, let me just draw it on my thumb. Huh? Let me just draw it on my thumb. Let's say you cannot imagine. Some of you cannot imagine very well. Let me just draw it on my thumb. Can you see the direction? Everyone? Yes, can see the direction. Yes. Now, what does this tell you? This tells you that when I point my thumb upwards, the current is flowing from the bottom to the top. Okay? So I can imagine that I have a conductor, a wire, and let's say that the current is flowing from the bottom to the top. What should I do with my thumb? I should hold it like this, because the direction is flowing, the current is flowing in the direction of my thumb, from bottom to the top. Okay? So I know I have to hold it like this. Now, because you must know, this can only go either direction. Okay, it can go up or it can go down. See? It can either go up or it can go down. So what happens is I will now let it go up. Why? Because current from bottom to the top. So I let it go up. Now, when I go up, what does it show me? What does this show me? Look at your other four fingers. What happens to your other four fingers? There is a direction to your other four fingers. You can see that whenever you hold your thumb up, you can see that the four fingers are curling in a particular direction, which is in this direction. Do you agree with me? If you look from the top, let's look from the top. Let's look from the top to your hand. You can see that they are curling in this direction. All right. Now we can call this direction, we call it anti-clockwise. Okay. Why? Because they are turning in the opposite direction of the clock. We call it anti-clockwise. Okay. This is anti-clockwise. That means the direction of the magnetic field lines will be anti-clockwise. So basically, using the right hand grip rule, your thumb is the direction of current. Okay, write this thumb down somewhere. You cannot remember things easily. And the other fingers, the four other fingers, okay, will be the direction of the magnetic field lines. Thumb, direction of current. Fingers, direction of magnetic field lines. So current going up, direction of magnetic field lines going anti-clockwise, which you can see is this situation. Right? Current going up, magnetic field lines going anti-clockwise. Correct? Correct or not? Hey, that's what you see. All right? That's what you see. Okay? That's what I have just shown you. Now, what if it's the other direction? Pointing downwards. What do? Of course, conductor. You're going to point downwards now. Hold it like this. Of course, during exam, you don't have this. You ever walk into the exam hall like this? You put it here like this, and then you bring to the exam hall. Never, right? Never, right? Anyone does this? No, right? Never mind. Don't need, okay? You can just imagine without the conductor. You will hold it like this, right? Even if you need, imagine like this. Okay? Your conductor. Where? Going down, you see? Now, when it's going down, what happened? You can see now the four fingers that are curling in the opposite direction. Look from the top. That's one thing you must remember. Look from the top. When you look from the top, you can see that the fingers are now curling in the opposite direction, which is in this direction. Now, you can see that this direction follows the clock, right? This direction follows the clock. So we call them clockwise. Okay? The direction follows the clock. We call them clockwise. All right? All right? So, in conclusion, the right hand grip rule tells you what? Right hand grip rule tells you the direction of the magnetic field lines. Direction of the magnetic field lines are affected by the direction of the current. Right hand grip rule, the thumb tells you the direction of the current, either that the current goes up or the current goes down. The other four fingers will tell you the direction of the magnetic field lines. Either it is clockwise or it is anti-clockwise. And they are always going to be in a circular shape. It will always going to be in a circular shape. So we call them clockwise or anti-clockwise. All right. So now you know how to determine. Now you know how to determine. Okay, the direction of magnetic field lines. Now, after that, what do you know? Let's look at the magnetic field lines. Can you see something very special in the magnetic field lines? The magnetic field lines, they are getting closer and closer to each other in the center. Why is it so? Why is it so? Why is it so? Because the magnetic field lines are stronger in the center because they are closer to the conductor. It is the same idea as the magnet. Whenever you are closer, Vishanta asked me a question. So if positive is bottom, the electric, let me see the Vishantan's question a while. I'll get back to you. Yes, Vishantan, you're correct. So Vishantan asked me, if positive is on the bottom, negative on the top, electricity will flow from bottom to top. That's correct. Because current flows from positive to negative. That's correct. Okay. So now let me go back to what I was explaining. I'm talking about the magnetic field lines, why they are closer to the center. Now, it is the same idea as the magnet. Whenever you are closer to the poles, they will get stronger and stronger. In this electromagnet, it's the same thing. Whenever you are closer and closer to the conductor, it will get stronger and stronger. All right. So that is why the magnetic field lines that are closer to each other in the center, understand? Because they are closer to the conductor. So if you look from the top, okay. So if you look from the top, what you can see is this. You can see that they will get further and further apart in the magnetic field lines. All right. Okay. So yes, that is regarding the electromagnet.